So straight out the gate, I want to say this is not a talk for people that are completely new to Git. You should have some familiarity with Git. Maybe it's your primary source control that you're using professionally. Maybe you've worked on some open source projects that use Git. The idea for this talk is to understand a little bit about the internals, how it works on the inside, and some of the more advanced workflows that you might want to use. So our focus is going to be on this beautiful object. It's not a new gender. It is the Git commit. It's an object of elegant design, beautiful in its simplicity, incredible in its power. And we're going to dig inside this guy and try and understand a little bit more about how it works and the kind of things that we can do. We're also going to talk about this guy, your typical developer. We don't really want to know the insides of this guy's mind. As you all know, when you're writing code, rarely do you do it in a logical way. It's a very creative endeavor, development. And so we're going to look at how Git can be used to tame the developer's mind, to allow us to rewrite history, to tell a story that is of use to the guy that's going to come afterwards, that's going to try and understand how code has changed. So let's start off with a quick recap of the typical workflow, Git workflow, that I'm sure you're all familiar with. The three commands that we use day in, day out. So the first of these is git checkout. This is how we get work out on the file system. So you might think of this, that the file is copied out of the repository and into the staging area. And then from there, it's copied down onto the local file system. And then we're going to do some work on it. And when we've done that work, we're going to use git add to copy that file back into the staging area and get our commit ready. And then when we're happy with all of those changes, we're going to use git commit to put the file into the repository. Let's drill in and take a closer look at that process. So I'm going to start by creating a simple file, and I'm using Vim to do it, not because I'm cool, but I want to make sure that the output is easily renderable just by catching the file out to the command line. So I'm going to make sure it's ASCII. Okay, so we're going to use a command called git hash object. Probably not a command you've seen too much before. And what that does is it shows us how Git is going to name the contents of this file. When it creates and stores it as a blob, we can go ahead and create a repository now. And in the usual way, we can add that greeting file to the repository and commit it. And there we go, we've created a commit containing that file. So let's just take a closer look at this. There's a command called git cat file, and that command needs to know what type of object from the Git repository we're going to display. And we're going to display a blob here, and then we need to give it the name of the object, and we only need to give it enough of the name to make it uniquely identifiable. And as we've only got the blob in the repository at the moment and not too much else, the 4 characters is going to be enough. And if we do that, sure enough, we can see the contents of the file out on the command line. Okay, so let's take a look at the commit itself. Up here we can see the SHA, the hash of the commit that's been created. And so we can say git cat file commit, and again just give it enough to identify that commit. And there we can see that the commit contains a tree. It contains information about who did the work and who actually committed it. Those names can be different if you're, for example, submitting a patch that's come in, a patch file that's coming over email from somebody else. Then you would see the author being the person that had done the code and the committer being the person that had added it to a repository. And then you can see the message as well that I created. And then we can drill in a little bit further and we can take a look at the tree that was created. And sure enough, you can see that that tree contains our greeting blob. And you'll notice that the name of the file greeting is separate from the hash naming the blob. And that's because the name of the blob is kept separately. It's only stored by the tree. And the reason for that is that if you rename a file, which is something that happens quite often when you're developing code, then Git doesn't need to create a new blob. It can just update the tree that holds that blob. The number at the front here, you may recognize if you're familiar with Unix operating systems. That's telling us what kind of a file it is, and 100644 is a file. You would see a different number here if, for example, it was a tree, and we'll look at that in a second. So one other point I'd like to make here is that this number returned by git hash object is going to be the same wherever we store that file. It doesn't matter what repository, where in the world we put that greeting file. If it has the exact contents that I created, it's going to have the same number. And that's one of the reasons why Git storage can be so efficient. By having this consistent naming, it means that duplicated data can be stored and referenced very, very efficiently. Okay, so now let's say that we wanted to organize our files a bit and store that greeting inside some kind of a child directory. Okay, here we go, we can see the changes. And let's just add those changes. And we've created a new commit. And we can see the history of our two commits if I just do a git log here. But let's look inside that new commit. So again, if we do git cat file and commit and use those first 4 letters, then we can see something that looks a little bit more like a typical commit. This contains a tree of files, just as it did before, but now we've also got a parent entry pointing to the parent commit, and you'll recognize that that's the first commit that we created. Most commits in Git, obviously apart from the very first commit, or it is possible to create new root commits. You have to do a bit of manipulation. You have to use some command switches that you probably wouldn't normally use to do that, but it is possible. So the vast majority of commits, 99.999%, are going to have a parent commit. And we can go and look inside this new tree that we've created. And there you can see inside, you probably recognize this, or you may recognize this from before as being the same tree that we had earlier when the greeting file was sat at the root. And that's because that tree hasn't changed. It's a tree that contains a single file called greeting, which has the blob that we had before. So here you can see an example of how Git is efficiently reusing its data structures in order to store information. And in fact, if we now just go and have a quick look on the file system inside the hidden Git folder. Then you can see, once again, you can see the shards of all of those objects that have been created. We've got files here representing the original greeting file. There's the tree that it was stored in, and here's the tree that contained the child folder, and the other 2 objects here you'll recognize perhaps as the 2 commits that were created earlier. So there's really no mystery here. What we're seeing is this highly elegant, simple and elegant system that Git has for storing information. And if you can wrap your head around this, then that's really the key to understanding everything about Git. It doesn't have a particularly nice user interface in the command line. It uses a lot of esoteric terms. It uses different names for the same thing sometimes. So if you keep in mind this really simple model under the covers, then you're going to find it much easier to navigate all of those commands. Certainly, that's the case for me. Trying to create this mental model gives you a really powerful tool for navigating what Git can do. So with that demo, you really have everything you need to understand how Git works. It really is that simple and that elegant. We have commits that point to their parents. Each commit contains this tree of blobs that describes the file system. Branches, unlike other source control systems where they are sort of a first-class concept that are stored in a special way, with Git they're really nothing more than a pointer to a commit. If it's a branch, that pointer is going to be updated as you add new commits into the system. If it's a tag, it's just a label for a commit that doesn't move. They're really that simple. Okay, so now let's try and simulate some more typical workflow within Git. So I'm going to start off and just create a file. There we go. You can imagine this is some kind of elaborate coding that we've been doing here. So let's add this file into a new repository. Okay, and then let's imagine that this is our master branch and we're a developer and we're going to do some work on a new feature 1. So I'm going to check out a new branch and we're going to do some work on this file. We're going to start working on our feature 1. So here we go, feature 1 is pretty cool, as you can see. And we'll take a little shortcut here and immediately commit that modified file just in one command with the AM switch. So we'll say that's add feature 1. And now let's imagine that we are another developer who is working on another feature 2, and they're starting at the same point on the master branch as the guy that was working on feature 1. And so they're going to work on feature 2, and there you go. Here you can see the file's in the same state as it was because we branched off of the master branch. So let's say that that's feature 2, and we'll add that in as well. Okay, so let's go back to the master branch now, and we'll just have a quick look at the situation that we've got here. So I'm going to use a custom log command. I'm going to show you how to knock this up later on. But if we do that, we can see we'll get a little graph that's showing us the master branch at the base here, and then feature 1 and feature 2 have both been branched off of that. Okay, so we're finished with feature 1, and we now want to add that work back into the master branch. So to do that, we're going to do a merge. And I'm going to specify here the no fast forward switch, and I'll explain what that's all about in a second. So we're on the master branch and we specify the feature 1 branch, and the merge has been successful. There are a number of different strategies that Git might choose to do a merge. So that first line is just telling us which strategy has been used, and the next line is just telling us that there's been a change of one line to file 1 line's been added, and then we get a little summary at the bottom. Dump out the contents of file 1, we can see that the master branch now contains the merged content. Okay, so this is the situation we created in code. We made an initial commit of file 1, forming commit A, and the master branch is pointing at that. And then we created a new branch, feature 2, and added in a change to file 1 to create commit X, representing the work of feature 1. And then we did the same thing, creating a new branch off of master, feature 2, and committing a change to that, forming commit Y. And then we specified a merge. We merged the work of feature 1 into the master branch, and we used the switch no fast forward. And what that did is it created a brand new commit B. It moved the master branch to point to that, and you can see that this commit, which is typical of most merge commits, has 2 parents. It points both to the feature 1 commit X, and back to where master was. And as I say, you'll generally be able to recognize the merge commit because it has typically 2 parents. It can have more than that, but typically it will have 2. Now in this particular case, there was no work done on the master branch while we were working on feature 1. So by the time we came to merge feature 1 into the master branch, there was no additional work that had gone on the master branch to integrate. And so we could have taken a shortcut. And in fact, Git will always try to take that shortcut unless you specify the switch that I did, this no fast forward switch, which will force it to always create a brand new commit when it does the merge. So this is what it would have looked like had we not specified no fast forward. All it needs to do to incorporate the feature 1 work into the master branch is simply move the master branch to the same location as feature 1. So let's go and redo the commit and see how we can achieve a fast forward merge. Okay, so here we are back on the command line, and I've issued my custom git log command to print out a little graph showing the current situation. You can see the master branch as a merge incorporating feature 1, and we're going to try and undo this no fast forward merge and do a fast forward instead. So the first thing we need to do is to get back to the situation we were in before the merge. And to help us do this, we're going to have a look at the ref log. The ref log, or reference log, is a black box flight recorder for Git. It runs in your local repository and it keeps track of where the special branch pointer head has been. So head follows us around as we move around, tracking the commit we're currently looking at. And so here you can see all of the work that I've done on this repository in reverse chronological order. So the first entry here is the most recent thing that we've done, which was the merge. And if we track down, we can look at the second entry here. You can see this is where we checked out the master branch prior to doing the merge, and you can see this A26B correlating with the original commit on the master branch. So if we were to move the master branch to point back to that commit, then it's going to be as though the merge had never happened. And so we have a few ways to refer to that commit. We can do it simply by number, or we could use the reference you can see here, these numbered special references, which are showing the historical locations of head. So I'm going to use the git reset command, and I'm going to use a switch hard, which says, I don't care, whatever the current work is that you have, throw it all away, move the master branch pointer to the commit that you specify. So as I said, I could do this just by referencing the commit, so I could do this, and that would work just fine. But another way of doing it is to specify this head pointer, and here there's a little bit of extra complexity because I'm using PowerShell. The curly brace has meaning in PowerShell, and so I need to escape it, and the escape character in PowerShell is the backtick. So if I escape these curly braces, then that's going to move the master branch pointer back to where it was. And you can see we get a little message to that effect. Head is now at A26B. And if I dump out this little diagram again, you can see that master is back at add_file_1. And if I tweak this just to show you where everything is, you can see we have the exact situation that we had before we attempted the merge. So now I can issue the merge again, but this time I'm not going to specify the no fast forward switch. And you can see that it's actually telling us that it's moving the master branch to point to the feature 1 commit, and that is in fact a fast forward. And then we have exactly the same modifications that we had before. So now if I dump out file 1, you can see it's exactly as we'd expect. And if I show the log file, then you can see that master and feature 1 are now both pointing at the same commit. Let's just look at the complete commit tree again. Here we can see that we've merged feature 1 into the master branch, but feature 2 is still based off of the old version of the master branch. It's based off of the commit that doesn't have the work of feature 1 inside it. So let's just remind ourselves what file 1 looks like on the master branch, and remind ourselves what it looks like on the feature 2 branch. Let's say that we now want to incorporate the work from the master branch into feature 2 as well. We want to update feature 2 so that we've got all of the work that's been going on while we've been working on our feature 2. Now, before we do that, we might be interested in finding out what that work is, just interrogating Git to see what work has been going on. We might want to use some comparison commands. So, starting with the log command, we may want to ask, what commits are there on the feature 2 branch that aren't part of the master branch? And so to do that, we can use the double dot syntax. So something like this. So that's going to say show me all the commits that are in the feature 2 branch that are not in the master branch. And unsurprisingly, that shows this single commit we've made on the feature 2 branch to add in the new feature. We might also be interested in asking what are all of the new commits that have occurred in both the master branch and the feature 2 branch that are unique to those branches, work that has gone on since the original branch commit, since the point at which we branched off the master branch. And to do that, we can use the triple dot syntax. And here we can see that we're seeing both the feature 1 work and the feature 2 work because those commits are unique to their respective branches. All right. So of course the other thing we might be interested in asking is how exactly have the files changed? And for those of you that are used to using Git, at this point you would typically be relying on some kind of diff tool, something like tortoise diff or beyond compare. But I'm just going to show you and go through what this looks like on the command line as well, so you can understand sort of the raw output that Git's providing for those tools. So the first thing we might want to do is say, can you just show me the difference between two commits? So I'm going to specify the master branch and the feature 2 branch, and this syntax would completely work and would be absolutely fine. But another way of expressing this is through the two dot syntax. So exactly the same command, just a different way of expressing it. So if I put this in, then we're going to see the Git diff file format, and this looks quite noisy, and particularly if it's much longer than this toy example that I've got here. But it's really quite straightforward what's going on. So let's just run through it. The first line is telling us that this is the Git diff output format. So it's a diff file, it's in the Git format. And then it's telling us what two files or what two snapshots we're looking at. So we have an A side and a B side. And on the A side, we're looking at file1.txt, and on the B side we're also looking at file1.txt. Now the reason why Git does this is because it's possible that we might be looking at a file rename or a file relocation, and in that case you'll see different names for the files here. Okay, so the second line of this output is telling us which two blobs are being compared. So this is a version of file1 on the master branch, and this is a version of file1 on the feature 2 branch. And then finally there's that number we've seen again, which is just telling us that we're comparing a file. The next two lines are a legend. They're telling us what symbols are going to be used to refer to each file. So we can see that this is telling us that a minus symbol is going to refer to the A version of file1, the version on the master branch, and the pluses are going to refer to the B version of file1, the version on the feature 2 branch. And then we're going to see a sequence of one or more hunks. So typically when you're doing a diff, your file is going to be arbitrarily long, certainly longer than this, and so Git won't show you the whole file in the diff. It's just going to show you the lines that have changed plus some context around them, and each one of those sections with the changes in the context is called a hunk. And so this is the header for the hunk. You're going to see two @ symbols, and then you're going to see the symbol for the left file, the minus here, and it's going to, the next number is the line that it's starting from. So this is line 1, and then you'll get and this is actually optional, a comma, and then the number of lines from that file that we're going to see. So this is telling us that anything that from the left-hand file we're going to see starting from line 1, we're going to see 2 lines, and then with the right-hand file we're also going to start from line 1 and see 2 lines. And then we actually get the contents of the diff itself. So we can see line 1, it has no lead annotation. That's telling us it's the same in both files, and the lack of a symbol at the front of that is also saying that this is purely context. So this is a line that hasn't changed. And then we're seeing a minus, so that's telling us that this is the version of the file that is in master. And then we're seeing a plus, which is telling us that this is the version of the file that's in feature 2. And then you can see if you add this up, we do indeed have 2 lines for each file. Now, if the comma and the number is missing, then that means it's going to default to meaning comma 1, i.e. we're just going to see one line from that file. Okay, so that's one kind of diff. That's when we're using the double dot syntax, which can be omitted. If we use the triple dot syntax, then what that is saying is, show me only the changes that I have added on the branch that I'm on. It doesn't matter if master has moved on. What Git's going to do, it's going to go back to the base branch, the branch that you originally came off of master from, or what's called the best common ancestor, and it's going to make a diff between that commit and the commit we're on, so we're only going to see the changes that we've added. And that's pretty useful if you just want to remind yourself what your changes are going to add in to the branch, to the master branch when you merge it. Then you can use this triple dot syntax. And so if we do that, now we can see that we're comparing against the commit we branched off of, and indeed we're only seeing the changes that have been made due to feature 2. Now let's go ahead and merge these changes into the master branch. So to do that, we're going to go to master and we'll say git merge feature 2. And if we do that, we get a conflict. Now that's not surprising, because what's happened here is both feature 1 and feature 2 have made a change in the same location of the file, and Git doesn't know how to handle that, because it's, it can't know. It doesn't know whether the change that you have made should replace the change that's been made by feature 1, whether they should both apply, or whether you should keep feature 1 in preference. So we have to tell Git how to do that. Now at this point, you might typically issue a command like git merge tool, which would go and launch a conflict resolution tool that you'd set up for Git. We're not going to do that here. What I'm going to do is I'm just going to show you how file 1 looks right now. And what you'll see here is it's been annotated to show the 2 conflicting lines, and it's going to give us then the option to resolve it. Let's remind ourselves what the commit tree looks like at the moment. Okay, so we're trying to merge feature 2 into master. We've got a conflict. Now let's have a quick look at where head is pointing. So this is going to tell us the commit char where the head pointer currently is. So you can see that the head has stayed on the master branch, the branch that we're trying to merge into. During a merge, there's a special branch pointer that's created called the merge head. So if we look at that, we can see that that's pointing to feature 2, the branch that we're trying to merge into master. Now any files that merge cleanly at this point are going to be loaded into the index file. So if we do a quick git status, we don't have any files that have cleanly merged. If we did have, they would be all staged and set up into the index. But we do have some unmerged paths. This is the one file that has a conflict, and it's saying both modified. So that means the conflict is because there are changes in both the source and the target branch for the merge. Now we can actually take a look at the index file here, and we'll see that it's recorded 3 versions of that file 1.txt. So if we do a little git ns files and throw in the use switch here, that's saying show us the unmerged paths. And what we can see, we've got 3 versions. The first version is going to be the version of the file that's in the merge base. Right, so the merge base is the commit, is this common ancestor. And then the second file is the version that's on master. And then the third file is the version that's on feature 2. Now these files would be copied and made available to your configured merge tool if you wanted to do the resolution with a merge tool. And then, as we saw, we have also the file that's in the working tree is the result of using the merge program. So if we open that up in Vim, we can see that we've got head, the master branch, the branch that we're currently on is indicators introduced with conflict markers pointing to the left. And then you have the dividing line, that line of equals, and then we've got the contents of the file on the target branch, and then that's marked with the arrows pointing to the right. We can resolve this conflict by editing this file. So I'm just going to remove all of the marker lines here, and we're going to leave the file like this, which in this case is saying that we want to have both the changes due to feature 1 and feature 2 in the result of the merge. And now that we've done that, the index still hasn't been updated, but file1.txt on the disk has been updated. So we can go ahead and add file1 into the staging area. And now you can see that our index file is all set up and ready to create the commit. And we can do a git commit. And without specifying a message, that's going to pop up my default editor, which is Vim in this case, to give us an opportunity to create the commit message. And I'll just accept that. And the merge is complete. Now you'll also notice at this point that it says recorded resolution for file1.txt. This is something you can turn off or on in Git. I recommend you have it on, and we'll look at the setting for that at the end. But Git has essentially remembered what decision we took in order to resolve the conflict of that file. And if now we have a look at the commit tree, we can see that we've created our merge branch, and this time it's had to create a merge commit. We had to make a decision to resolve that conflict. We couldn't, there was no kind of fast forward that was possible. So we have a merge commit. We can see we've got a merge commit from the two parents, and we can see that it's incorporating now both the changes of feature 1 and feature 2, and it's incorporated them in the way that we instructed Git to incorporate them. And in fact, if we go and look at that commit, we can see that we have our tree as always, and you notice that we have 2 parents now. And it's worthwhile just pointing out at this point that if you are trying to look at log history and you're trying to specify the log of commits, there's a couple of ways that you can refer to the parents of a commit. But let's just have a look. If we say show me head, that's obviously going to show the commit we're on. We can see the entry, the resolution that we've just made. If I wanted to have a look at a parent commit, then I have to tell Git which parent I want to look at. So if I use a single caret at the end, that says show me the first parent, and the first parent will always be the commit that has come from the branch that you were on when you did the merge. So this is going to show the mainline side. And you can see here, this is the feature 1 change, which was the change that we already had in on the master branch when we started this merge. And if I use the number 2 here, this is going to refer to the second parent from the current commit. And there we can see it's gone down the other side now, and it's just showing us the commit from the feature 2 branch. This is one way to go in order to incorporate the changes of feature 2 into master. Let's have a look at another way of approaching this. So this is the merge that we have just done with feature 2. Right? We wanted to merge the feature 2 changes into the master branch. So we've created a new merge commit that has 2 parents, one parent pointing to the master branch and one parent pointing to the feature 2 branch. Now in this case, that's not a particularly complicated looking commit diagram. But if you imagine that you're in a team working with multiple developers, it wouldn't be uncommon to be working with 5 to 8 developers, make a typical size team these days, but it could obviously be many more than that. If you can imagine how complicated the merge trees might start to look with that many developers working in parallel, this is when we want to start thinking about rewriting history not to record exactly how the changes were made as they happened, but in order to create a story that communicates logically how the code has changed over time. And that's where we can turn away from merges and look at the rebase. We can see the result of a rebase operation on the left-hand side here. And what rebase does is it rewrites history. In this case, we can see that the Y commit, the original commit made when working on feature 2, was made from an earlier point in master. Since we created that branch, master moved on. It gained commit X, which represented the work in another feature. And we're going to create a new story. We're going to create the story that pretends that all the work of feature 2 happened after feature 1 was merged into the master branch. Commits, though, are immutable. They can't change, and in fact part of their definition is their parent or parents. So you can't simply update a commit and change its parent. That you're not allowed to do that. You have to create a brand new commit, and that's what's happening here. So this Y prime is the equivalent of the change made in the Y commit, but set so that the tip of the master branch is its parent. What Git is going to do is it's going to work out the patch, work out the change that occurred between commit A and commit Y, and apply it on top of commit X to create a new commit Y prime. And once you're in that position, you have the situation shown on the right hand side here, where merging feature 2 into the master branch simply becomes a fast forward merge. So the first thing we're going to need to do is undo the merge that we just did. So we can move the master branch back to its first parent. And if we just show the commit tree again, you can see that we're back where we were, and feature 2 has not been incorporated into the master branch. So let's try rebase. So let's move on to the feature 2 branch, and then we're going to say rebase onto the master branch. And we get a lot of output. What's happening here is that we still have the same conflict to deal with that we had to deal with when we did the merge. So let's run through this output. So the first line here, we see first rewinding head to replay your work on top of it. So what that's saying is that Git is going back to, in this case, the point at which you branched off of master, the common ancestor of the master and the feature 2 branch. And it's going to apply a patch equivalent to each commit that you have made on that branch. So there's only one commit here, the work that we did in feature 2, and it's going to look at it's going to create a diff between the parent branch, the parent commit, and that commit that you made on feature 2, and then it's going to apply, and that's the second line we see here, it's going to apply that change, that patch, onto where the master branch is now. Okay, the next line we see, it's modifying file 1 using the resolution that Git has remembered from when we resolved the conflict, this same conflict previously. Right? If you think about it, Git is still trying to push together exactly the same two changes, the two conflicting changes that we had before. In the same way that we saw with the merge, if we hadn't have had this, then the file1.txt on the disk would have been marked up with conflict markers. But in this case, it's applied the resolution that it's remembered, and so file 1 has been fixed up in exactly the same way. The next few lines that we see is just sort of showing a log of how it attempted to do the merge that conflicted. It's found the base of the merge, and it's tried to use a three-way merge to resolve the conflict, and then it has conflicted. it put the merge conflict markers into file 1, and then it's saying patch failed at 0001. That means that the very first commit that it tried to apply in this rebase, and there is only one commit here, is the one that failed. It's telling us it's made a copy of the patch, so the exact diff between master and the feature 2 commit. It's made a copy of that patch and it's recorded it for us, and we now have the opportunity to go and resolve the problem. Okay, so let's just clear the screen for a second, and let's remind ourselves what the commit tree looks like. Now, when you're dealing with a rebase, when you're sorting it out, you'll quite often be resolving conflicts and doing a bit of work, and it's always worth knowing that the git status command will give you a very good description of exactly where you are in the process and what commands you need to issue to carry on. And in this case, you can see it's telling us that we're in the process of rebasing onto the master branch here. It's telling us which branch we're moving. It's telling us how to skip this particular patch. So if we want, we have the option of not applying a patch in the rebase, and it's also telling us how to get out of the rebase altogether, and that's going to sort of put things back to how they were before we started doing the rebase. And then we have very similar output to the output we had when we were resolving the merge conflict first time round. So a couple of things here. First, I just proved to you that file 1 has been resolved using that recorded resolution, so you can see that it's been already fixed up the way that it was previously. Second thing is I'm just going to show you an alternative syntax for looking at those unmerged files. So I use the cat file syntax to dump out the copy of the 3 versions of file 1 here, but just so you know, you can also do this, so that the colon and then the number of the index of the file. So remember, 1 is the ancestor, common ancestor, and if we look at 2, that's showing us the original version of the file, sort of before the patch that we're trying to apply was applied, and then the work that's gone on the feature 2 branch. So we've already got a resolved version of the file, so we can go ahead and add that into the index. And then if we do a status again, we can see that Git's going to tell us that all the conflicts are fixed, and this time we need to issue a slightly different command to carry on. We can say git rebase continue, and then it successfully applies the patch, and as that was the only there's only one commit that we had to rebase, we're done. And now if we issue a log to look at the commit tree, we can see that we have this lovely linear story. We've now created a new commit representing the work that we did in feature 2, and it is now on the tip, so it has master as a parent and so on. So we have this nice clean line. Now it's not telling the story of exactly how the work was done, but it's giving us a much easier to read story, a logical story. And notice that the rebase hasn't changed master. We're now in a position to do a fast forward merge on master if we wanted to. So I could check out master, I could say git merge feature 2, and we would get a clean fast forward merge. But I'm not going to do that. And this is typically the process that you're going to want to do if you're working on a feature and it's taking a few days, and your master branch is changing, every day as work comes in from other teams. Then you'll generally want to take the time out to rebase and incorporate the latest changes from other people's work that is finished, so that you can test your feature against the latest version of the code. Okay, so let's look at a little bit of a slightly more realistic workflow. Let's say that in fact we're not finished with feature 2 yet. We need to do a bit more work. So having rebased, I'm going to open up file 1, and let's say while I'm looking at file 1 that I find there's a problem and I need to put in a bug fix. It's not uncommon. You spot a problem in the code and you fix it. and then I carry on doing some work on feature 2. Now we've got a change that really represents two logically different things that we were trying to do. What we'd like to do is to record those as separate commits so that we can prepare a nice story to tell when this work is done. And we can use a version of git add called the patch add, which allows us to decide interactively what work we'd like to put into a commit, picking out individual modifications to a file. So when I issue this, then we're going to see the familiar diff format, and here we're comparing our working tree, our file system modifications, against the original version of the file stored in the index. We can see here this hunk format. We can see that we're looking at line 1 of the unmodified and the modified file in both cases. We're showing 3 lines from the unmodified file and 5 lines from the modified file, the one on the disk. And we're being asked, do we want to stage this hunk? Do we want to put this difference that we're looking at into the index? And we've got a number of different options here. If you bang in the question mark command, then it's going to spell out exactly what those changes are. So we could say, yes, stage this hunk, put those changes. In fact, we're seeing both changes in the diff file there, put them both into the index. Or don't stage this hunk. No, we don't want to put this into the staging area. We could abort the whole process. If we pick in A, all, then we're going to say from wherever we've got to take every other change, this change and every other change in the file, and put them into the index, and so on. Now, there's an interesting command here, split. And that's what we're going to do here, because we can pick that when the hunk that gets selected for us is too big and contains, as it does here, changes that we would like to split into different commits. So if I issue the split command, we're now being presented with just one of those changes. And I am going to stage this hunk, and then I'm going to say no more. So let's quit out of that. And at this point, if I issue a git status command, we can see that file 1 is now modified both on the hard disk and in the index. And the changes in the index are just the changes for fixing the bug. And so I can prove that by just doing a quick diff, and the -- cached switch says compare the staged version of file 1 to head. And so we can see that in the index we've just added the bug fix. So now if I go ahead and do a commit, I can say that was fixing the bug, and now what's left is the other change that we made. So I can now add this into the index, and this is finishing feature 2. Okay, so now if we look at the work that we've done, we can see all of our work is in separate commits, but it's not a nice story, right? But making fine-grained commits like this, each of which contains a logically distinct piece of work, we've set ourselves up nicely for being able to rewrite history to tell a nice story. And to do that, we're going to use something called an interactive rebase. And I specify an interactive rebase by using the -i switch. And I'm going to say I want to rebase feature 2 interactively onto master. Now, when I do that, Git is going to give me a set of instructions to edit that I want Git to carry out in order to reorganize this branch. By default, those instructions are simply going to be to use every commit that I have specified in the order that I created them. So we can see at the top here, the oldest commit. So this is the first commit I made on top of master, and so on down through the file. And we can see here that we started off by making a change to add feature 2 into the file. Then there's a commit where I fixed the bug. And finally, there's the commit where we finished off feature 2. But what I'd like to do is get that bug in as fast as possible. So I'm going to remove the pick line where I fixed the bug, and I'm going to put it back in at the top of the file. So that's an instruction to Git to use this patch to make the first commit that's going to come out of our rebase. And then I'm going to go to the last commit. So we've got 2 commits that come after that where we're working on feature 2. And although I did those as 2 separate commits, that's not the story I want to leave behind. For me, it's a fairly simple atomic piece of work. I don't need to split it up into separate pieces. In fact, it would be a better story if I just combine this into a single commit. So I'm going to change this from a pick command to be an S for squash. And you can see in the comments section of this file that Git spells out the possible commands that are available to you. And I think the descriptions there are fairly self-explanatory. So what squash is going to do is it's going to mean that we're going to apply the patch for adding feature 2, but then we're not going to create a commit at that point. We're then going to apply the patch for finishing feature 2 into the index and then create a commit, a single commit, all in one go. And so at this point we're done. We set up all our instructions for Git, and we're going to quit out the dialog, and Git's going to run through and apply all those commits. And it's thrown up the editor for the 2 commits we squashed together. It didn't throw up the editor for the bug fix because that was a single commit, and because we told Git we just wanted to pick it, we didn't want to reword the commit message, it's just gone ahead and applied the patch. But now it's showing the commit messages from both of the commits that we're combining. It's giving us the opportunity to create a commit message for those 2 commits. Now I don't really want to show sort of the evidence of working on this as 2 separate commits. I don't need to do that. You may want to. If you've got a whole series of commits, you might want to combine those messages into a descriptive log message, but not necessary here. So I'm going to remove those extra lines, and the rebase is finished. And if we look now, we have our beautiful lie telling us a nice story of the logical changes that happened to the code base. And if we want, we can check out the master branch and we can just merge in the bug. And that's going to be a simple fast forward merge. We look at the commit tree, we can see that master has now incorporated the bug fix, and maybe there's some more work to do on feature 2, or maybe we can go ahead and merge it now. So that's interactive rebasing. Okay, let's change tack entirely. So hopefully we're now armed with some newfound understanding and confidence around how Git works, how this map of commits fits together. So I'm looking at now some sample code written in Visual Studio 2017. The source code that you're looking at is available from my GitHub repository, and I'll put a link up at the end of the presentation. This code is using a NuGet package called libgit2sharp, which wraps up the C Git libraries, makes them available in a nice friendly way to C#, and lets us do some interesting things. The first thing I want to do is just show you this routine: get CS files, new or changed, at head. This file is going to send us back an IEnumerable of tuples. We're using the new C#7 named tuple syntax here, and each entry is going to contain a path for the file that we are looking at, and then it's going to contain the contents of that file. In the previous commit, it's going to be empty if it's a new file, then the contents of the new version of the file. So here we're looking at an instance of the repository object that's come out of libgit2sharp, and we can walk this. We can go into the head, we can look at the commits starting at the head and pluck out the first commit. So that's going to give us the commit at head. The second line here similarly is going to give us the first parent of that head commit, and then we're going to use the static diff function to compare the trees of those 2 commits. So that's going to give us a list of the changes, specifically a list of the paths that have changed. Then we're going to filter that list to give us the list of files with the .cs extension, i.e. the C# files. And then from that we're going to select what we need. So we're going to grab the file path and then use the get blob contents or empty string helper function to actually put out the contents of those files and return them. And so you can see the helper function here just below that. It takes a blob ID. If the blob ID is null, which is going to be the case if this is a brand new file that didn't exist in the parent commit, then we're just going to return an empty string. Otherwise, we're going to look up the blob and we're going to pull out the content and we're going to return that back. So this helper file is going to basically give us a list of all the files that have changed with their old and new versions. So let's see how we can use that file and combine it with the power of the Roslyn compiler. So what we want to do is look at the commit at head, pull out all the C# files that have been added or changed, and print out all of the new methods that have appeared in the file. First line, we're going to pull out all of the C# files that have changed. Then we're going to use a helper method to get a count of all of the methods in those files. So what that's going to bring back is a little dictionary, a little lookup. It's going to have the name of the method and then how many times that method appears in the file. So let's just have a quick look at how that works. So here's our get method counts helper method. You can see it's going to return us the name of a method and the number of times it's appeared, and it's going to work on a C# source file. So first line of code, we're going to use Roslyn to create a syntax tree for that source code, and then we're going to do some link over the syntax tree. So we're going to start from the root of the syntax tree and go into the descendant nodes, and specifically we're going to pick out all of the method declarations in that file. And then once we have the method declaration, we can walk into that and we can pluck out the name of the method. So we're doing that for all of the methods in the file. So we're going to group by method name, and then we're going to make a count of the number of occurrences of that particular method name. And then we're going to return that back to the caller. Okay, so we're going to do that for both the old file and the new file. And then we're going to use a bit of link to join those two counts together and subtract them from each other. So we grab the counts from the new file, the counts from the old file, we join them on the method name, and then from that join, we calculate the difference in the numbers of occurrences of the method name. So again, we're creating a tuple here which contains the method name, and then a count which subtracts the difference. And then what we're interested in is new methods. So in that case, the delta, the number of occurrences of the new method versus the number of occurrences in the old method, is going to be positive. And then we just simply select out the method name and put that out to the console. So I'm not going to show you that running because the output is obviously going to depend on the code that we pass it. I encourage you to download the code and try that out for yourself. And hopefully that might inspire you to think about how you can use Git to query your source code for interesting information. So my intention here is to inspire you to think about what Git can tell you. There are lots of interesting questions which we can ask our source code, and I'm not talking about sort of the corny big brother lines like who's the most productive developer. Lines of code are never a good measure of that, but it can answer some interesting questions. Particularly for me as a consultant going in and looking at new code bases, it can very quickly give me some insight which can take a lot longer without tools like Git available. So I can answer questions like, where are the most bugs in the code? With most source control systems, the work that you do, the messages that you apply to the commits that you're making are typically linked back to some kind of work item control system. And so you'll often find bug numbers in the commits. So if you have bug numbers in the commits, then you can identify the commits that are fixing bugs. And with tools like libgit2sharp, we can see what files are involved in fixing those bugs. And then we can use that information to create a map of where those bugs are within the system. So we can find out what are the most buggy areas of code. Perhaps they're worth more of our attention. And although we might not be interested in the code line productivity of each developer, because it's code quality that's important, right? Not how much code you produce. We might be interested to know what's the bust factor of each developer. What knowledge might be walking out the door if a developer chooses to leave? So an analysis of what files within a large code base a developer is working on and how much that overlaps with other developers in the team can give us that kind of insight. If we go a bit deeper and start to parse the code with tools like the one that I've just shown you, we can look at things like method names and variable names to understand the language of the code and get an understanding of what kind of functionality that code is delivering to the business, and ask ourselves questions like, are we working on the things that are most important to the business? So here's a few links for you that might be useful. The first one is just where you can find Git for Windows to install. You may have noticed during the presentation as well that my prompt was annotated with information around the current branch that I was on and the files that had changed both on the file system and in the staging area. That's done through an extension for PowerShell called PoshGit, which you can find at the current location, and the easiest way to install that is through Chocolatey. The next link is for Console Z. That was a console application that I was using to present Git. It's quite handy for giving you a bigger font, and it also has a really nice customization for colors, and particularly when you're trying to show those commit diagrams, some of the colors can be very dark, so the ability to edit those is really handy. So you can find Console Z at that location, and again it has a Chocolatey install I'd recommend. The NuGet package, which allows you to get access to Git commands from C# is called libgit2sharp. The Roslyn APIs can be found documented, and the source for those is also available at that location. And then finally, the demo code that I show is available on my GitHub at the link there. Throughout the presentation, I was using an alias that I created, the git-lg command. It's not part of Git, so it's a customization. If you want to use that to be able to print out the nice sort of graph of Git commits, then this is the command that you would need to enter to add the alias to your global Git configuration on your machine. So I hope you've enjoyed that brief exploration of some of the more advanced features of Git. If you want to get in touch, then do follow me on Twitter or look me up on LinkedIn.